Assalamu alaikum students. In today's lecture, we will learn about some of the remaining part of bond length. Then dipole moment will be discussed, including next onward the numericals related to the dipole moment. Then ionic versus covalent compounds comparative study will be there. And then we have the different types of crystal structures to be discussed. Now students, in the previous lecture you have learned about the bond enthalpy and the factors on which it depends upon. Bond enthalpy is the amount of energy which is required to break or make one mole of the bonds, or the factors on which depends upon, that is the atomic size, electronegativity, bond length and bond order. We have discussed them all one by one. Some more aspects of bond length should be discussed here, depending upon that of the what is meant by bond length, how it is affecting that of the polar or non-polar molecules, or what you say, what are its effects on the bond energies. A little bit of it is further given here. Now students, today we have to discuss the aspect of whether the homonuclear or that of the heteronuclear, or you can say the polar or non-polar molecules, they have the similar one bond lengths, or whether this polarity is going to affect the bond length of the substances, so that bond energy will also be affected, right? So for this reason, here you can see in the diagram there are present two homonuclear atoms which are joined together by means of a covalent bond. The half of this distance is termed as the covalent radii. Now, uh, turn it, what to say, or apply it on that of the HCl molecule. Suppose on HCl molecule, here it is given. It comes out from H2 and that of Cl2. For example, the radius which is found of hydrogen in the H2 molecule and the radius of chlorine found in the molecule of chlorine molecule, right? Chlorine as a gas, right, in the diatomic molecule. Here if we join the one of hydrogen and one of Cl, whether the bond length shared by two in this molecule is same as that it was being present in H2 for hydrogen and Cl2, the chlorine atom, for chlorine atom. So the sum of these two will give the theoretical value of the bond length present in HCl. When it is determined experimentally, it is found that there is a difference between these two. And when it is found being done similarly, means bond length is affecting the bond energy, right? So the bond energy of HCl was found experimentally high as compared to being present in the observed, or you say in the theoretical value found for hydrogen and chlorine, right? It is given in your book that where the relationship between bond energy and polarity, or the strength of the bond and its ionic character is being discussed, in which the calculation of bond energy contribution of one hydrogen atom and that of one chlorine atom from H2 and Cl2 are considered, and then by joining these two, the bond energy, that is the theoretical one, is calculated for the 1 mole of HCl bonds, right? Now this is the theoretical value only. If we calculate it by means of the experiment, then there is a table given in your book as well, table 3.3, where it is given the comparison of experiment and theoretical bond energies. You will find that for the HCl, the bond energy is 431 instead of 338.9, which is calculated theoretically. So why there is such a difference between? It means the polarity between these two is responsible for minus and plus signs are there on chlorine and hydrogen respectively, the partial ones, right? So that this polarity makes them to be closer, and smaller is the size of the bond length, so greater will be the amount of energy, as I have told you earlier. So that's why we say the polar molecules, they have the larger values or the greater values of bond energies as expected from their theoretical values, when this is calculated from their respective molecules or the respective existence, right? Now, next one, here it is given some of the covalent radii which are discussed here. All these are the homotypes. You will find there the bond lengths are given, that is carbon to carbon bond length, carbon to carbon double bond is present, and carbon to carbon triple bond is present. Look at the difference between these all. Carbon to carbon there is 1.54, then it is reduced in double bond, then more is the reduction in 1.20. It means now you are able to answer it why there is such a difference and how it is affecting the bond energy. Yes, the carbon to carbon single bond means less amount of energy is required and the bond length is large. But if I say carbon to carbon triple bond I have to break, so I will need greater amount of energy as the bond length is short. Right? Same is here for the other one atom. Now you can see here once again carbon to nitrogen. Now there is a difference of electronegativity between carbon and nitrogen. You can see, compare it with that of the carbon to carbon bond length. Carbon to nitrogen bond length is quite different and smaller than that of the carbon to carbon bonding. Right? So what does it mean? Means carbon to nitrogen bond is more strong as its bond length is only 1.43, while in case of carbon to carbon it is 1.54. So the bond energy of CN bond is larger as compared to carbon to carbon. Right? Same is here for the carbon oxygen bond, and then we have the carbon to oxygen double bond, or maybe carbon to nitrogen double bond or triple bond. In the similar manner they are comparable to that of the carbon to carbon double bond and carbon to carbon triple bonds. You can see greater is the difference when we have placed oxygen along with that of the carbon, because the electronegativity of oxygen is much more higher than that of nitrogen, so the bond shortage occurs more here, right? So this is how we say the bond length is affecting the bond energy, and it is more affected when there is present polarity in the molecule. Right? Now come to the next one here. The hybridization also affects the bond energy. This is how. Again, it is related to the bond length, and then bond length is ultimately related to that of the bond energy. Here you can see carbon to carbon there is present sp3 hybridization. Remember it. Whenever carbon is linked singly with the other carbon atoms or the other atoms by single bonds, carbon is sp3 hybridized. Right? So the bond length is being 154 as we have done in the previous slide. Bond energy is given, bond length or bond strength 346 kilojoules per mole. When we consider carbon to carbon double bond, the hybridization mode changes. It is sp2 type, and then we have the bond length reduced to 134, which is due to the double bond in it. Right? And the hybridization is sp2. Right? The character or the percentage of S is being increased. You can see the S character and P character means the S orbital and P orbital ratios. They are comparable in carbon to carbon single bonding. There is 25-75% ratios, while in sp2 it is 33 to 66% ratios. As the S character is increasing, so that bond energy is also increasing. Here you can see it is near to the double of the above value when there is present a double bond between carbon to carbon with sp2 hybridization. And when there is present sp3 hybridization, sp hybridization, that three bonds between carbon to carbon, the character of S and P becomes 50 to 50%, equal character is there, and once more the bond length being reduced up to 120 with the bond strength increase from 612 to 835. Right? So this is how the bond length is affected by the number of bonds or the bond order between the two atoms, as well as the hybridization in the carbon atom or the other atoms as well. Now students, the next topic is of dipole moment. Dipole moment is actually the determination of the degree of polarity of molecules. You should come to know first what is meant by polarity. Polarity is given by that of the, what you say, the when two dissimilar atoms they are joined together by means of the covalent bond, they can give rise difference of electronegativity between them, on the base of which the two of the atoms they acquire the charges on them. That is, one will acquire partial positive, another will acquire partial negative charge. As you can see, it is given by means of this example here, where the hydrogen and fluorine they are linked together by a covalent bond. Hydrogen with the small size and less electronegative value is present here, while fluorine with the larger size and then that of the high electronegativity, it is bonded here. Now what happens, the pair of electron which is shared between them is attracted more towards that of fluorine. So we can say there is movement of electrons from hydrogen towards fluorine. So we direct an arrow from hydrogen towards that of an fluorine atom, right? This will give you a vector formation, right? There is a particular direction, so we represent it by means of a vector. By doing so, the hydrogen acquires a partial positive charge as it is given, this one, while the fluorine acquires a partial negative charge. So we say there is a creation of a dipole, and we say this molecule is a polar molecule. Remember it, dipole moment is only being determined for the polar molecules. For non-polar molecules it is 0. Means if we say hydrogen to hydrogen, the pair of electron will be equally attracted by both the atoms, and as they both have no difference of electronegativity, both have same size, so they will attract equally the pair of electron between them. So that's why I will say there is no dipole moment present and no polarity will be there in that molecule in the similar atoms joined one, while the dipoles will appear where there will occur the difference of electronegativity between the bonded atoms, right? Now here the dipole moment and its units are being given. The quantitative measure of the polarity of a bond is called dipole moment, which is represented by mu. Mu is equal to the Q into R. It is the what you say, the product of charge of an electron, a unit charge, into the distance between the two bonded atoms, right? Or the distance between the two charges. So you can calculate it. Two of the units which are given for the dipole moment are coulomb meters, and the second one is debye. Coulomb meter is the smaller unit while debye is the larger unit. Now here how it is being calculated, it is given that the unit charge on an electron is 1.60 into 10 to the power minus 19 coulombs. Suppose the distance by which the two charges are apart, that is 100 picometers. So multiply this value with the Q. For to find out the result in coulomb meters, convert this picometer into meters. So multiply 100 to the 10 to the power minus 12 meters, right? So the value will come out 16 to the 10 to the power minus 30 centimeters. Now here the larger value of the dipole moment is debye. The relationship which is used here, it is 3.336 into 10 to the power minus 30 coulombs meter is equal to 1 debye, right? Once again, it is 3.336 into 10 to the power minus 30 coulomb meters, that is equal to 1 debye, right? So by using these two units, we can find out the dipole moment of the substance. Now here some of the applications of dipole moment are given. The first one is the determination of the polarity of the molecule, whether the given molecule is polar or non-polar. For this you must remember the previous one theories which you have done, especially the hybridization, that the mode of hybridization present and the geometry which is held by the molecule in the different one example you have done previously. Now look at the first one. That is example. It is given for the water molecule. You know very well oxygen, and it is sp3 hybridized. Four of the orbitals will be formed, which are hybrid orbitals, and it will give the shape of the angular one form, or the bent one form, or the V form, as the two of the what to say, the hybrid orbitals, they are filled with that of the non-bonding electrons, right? Now here you know very well oxygen is more electronegative, so the pair of electron is more attracted towards oxygen from hydrogen. It is a dipole. So what we say, what will be the direction of the vector? Here it will be directed from hydrogen towards this oxygen from both sides. Now, use the head to tail rule to sum up these vectors. There will be some value appear for this molecule, so it is considered as a polar molecule, right? What about this? Look at this. Here it is carbon dioxide. Carbon dioxide have a linear geometry. The carbon in it is sp hybrid, right? So what happens? It is going to make double bond with one oxygen and double bond with the other oxygen, which are placed at the angle of 180 degrees. So what happens? Look at this carefully. We say the two vectors will be directed from. Now tell me which one is more electronegative. Definitely it is oxygen. So the vectors will be directed from carbon towards that of the oxygen. As the two atoms are similar, the two atoms, they will have the opposite direction, but the magnitudes are same. So the sum of these two will give rise to zero value. So you can say for this geometry, that is linear geometry, when two similar atoms on both sides are attached, the value of dipole moment will be zero, as the two vectors will cancel out each other's effect, right? This is how we can determine the molecule is polar or non-polar. It means water is a polar molecule while carbon dioxide is a non-polar molecule on the base of the value which is given in the form of dipole moment. Similarly, look at these two compounds. One of them is CCl4, carbon tetrachloride. The other one is chloroform. You can see in carbon tetrachloride, in the central carbon is sp3 hybrid, and the four atoms which are chlorine atoms, they are directed towards the regular tetrahedral geometry, right? When they are present in so, we can see due to the difference of electronegativity, arrow is directed from, or the vector is directed from carbon towards chlorine, right? So now the sum of these four vectors will give rise the value of dipole moment 0. Once again you can see the linear geometry, it is having 0 dipole moment, as well as the tetrahedral geometry, when all the four atoms joined are similar, again the dipole moment will be 0. But what happened when we have changed one of the chlorine by means of H, right? Now this vector will be cancelled by this vector, but this vector cannot be cancelled by this one, as the length will vary, as the magnitude, direction is opposite, but the magnitude will be different, as the atom is different. From here the arrow will be directed towards carbon, right? While all the others, in them the arrow will be directed from carbon towards that of the chlorine. So it will have some dipole moment in it. The sum of the vectors will not give rise the value 0. So it is given, it is 1.92 coulomb meters of that is the dipole moment, or debye it is given actually, not coulomb meters. Okay, now this is how to determine the polarity of molecules. Next one slide tells you that if you have the cis or trans structure, now it is the geometry which is the spatial arrangement, that is the three-dimensional geometry in space of the different substances. Two types of the molecules are possible. We say there is present a geometrical isomerism. that is when the two carbons, they are linked by means of a double bond and they have attachment of different groups with them. So we say these double bonds, they restrict the free movement of the groups attached on it. So we find there are two types of the structures which are present in the compound due to their spatial arrangement. So one is termed as cis type. You can see this one is cis type when the two similar groups are present on the same side. Here it is carbon and chlorine to chlorine. Right, they are present on same side. It is called as cis isomer, and when it has the opposite sides, it is termed as the trans isomer. When these two are present like those, we say they are related to that of the stereochemistry. Geometric isomerism tells you about the geometry of the molecules present in the three-dimensional when there is present a double bond between the two atoms of carbon which are further attached with the other different atoms with them. Right? This is the branch of the stereochemistry actually. Right? Now what happens here? Look at this. The substance which is cis, it is having the direction of the vector from carbon to chlorine. I think you know very well now why it is directed towards chlorine due to greater electronegativity. When you add these two vectors, the dipole moment has some value. It is 1.9 D. D is represented by, right? So what happens there? There is present dipole moment. It means this molecule is polar. When we say it is trans type, now you can see here the movement of one of the chlorine to the other side. So the pointed arrow is directed oppositely in the structure, and the both of them, as they are of the same length, same distance is covered, and they have the same magnitude, but the direction is opposite. So the cancellation will occur and the dipole moment of this trans isomer will be 0. The molecule given here is 1,2-dichloroethene. Both of them are same. Molecule एक ही है, but the arrangement of these molecules in the space, they are different. ये ऐसा ही है जैसे आप बलून पकड़ के हवा में उनको कर दें, जो गैसी जो हाइड्रोजन फिल्ड बलून्स होते हैं उनको आप हवा में छोड़ें तो they will get or they will acquire a shape in it. ठीक है, तो वो जो ज्योमेट्री कहलाएगी वो 3-dimensional ज्योमेट्री कहलाएगी in the space. Right? Now come to the next. Now the next one given is the determination of the percentage of the ionic character, that how you can calculate that the given substance is having some ionic character or how much it has, how much percentage of ionic character is present in it. Let's consider for the hydrogen fluoride. Theoretical values is given for that of the bond length is mentioned here, that is 92 picometers, that is the distance or the R between that of the one of the charges, that is hydrogen and fluorine. It is the bond length, and then the dipole moment is being found. It is the value which is experimentally calculated. This one 1.92. D is the observed one value or experiment value which is calculated one, right? Now we have to find out the theoretical value that will be termed as mu ionic, right? The formula applied for the ionic character determination is percentage ionic character. This is equal to mu observed, means experimental value, divided by mu ionic. Mu observed is given as 1.92 D, or mu ionic we have to calculate. Now how to calculate it? Calculate it by means of the values given. You know very well the charge, that is 1.60 × 10⁻⁻19 coulombs, and that of the distance is given, multiply it, but before it you have to convert it picometers into meters. How? By multiplying it with 10⁻⁻12. Right? After doing so, what you have to do, you will get the answer in coulomb meters. Now get the relationship between the two. It is 3.336 × 10⁻30 coulomb meters, which is equal to 1 by. So calculate it in dBi as the units should be same. The observed or the experimental value is given with D. So convert it also into dBi. Right, the value will be 4.42 dBi. It is calculated in your book. You can see that here when we have divided it, the value is 0.43. 0.43 means out of the 100%, there is only 43% ionic character which is present, while the 57% it is covalent character is present. So we say it is a covalent molecule, but it has some ionic character in it. How much? 43%. Right? This one is how to calculate the ionic character in the molecules which are covalently bonded. Now here the effect of bonding on the properties of compounds being explained. Here the solubility of the ionic compounds. You know very well ionic compounds, they are formed of cations and anions which are held together by means of electrostatic force of attraction between these anions and cations, and they are present in the form of crystal lattice, right? A three-dimensional geometry, three-dimensional structure. When they are dissolved in water, what happens? The bonds between these cation anions, they are broken, and the attraction between water molecules and that of the oppositely charged ions, it develops. The oxygen of the water will attract the positive ion, while the hydrogen atoms will attract the negative ion due to the opposite charge. Right, so there will be appearance of the hydrogen bonding. The energy at this moment which is released due to the bond formation between that of cation and anion and that of the water molecule, it is termed as hydration energy, and the energy required to break between these two, of that type of the ions, that is positive and negative ions, it is termed as lattice energy. If lattice energy is low and hydration energy is high, the substance will dissolve. And if lattice energy is so much high and hydration energy produces very less, substance will not dissolve in it, right? The energy which is released is termed as hydration energy, as it is the attractive force developed between the ions and water molecules, while that of the lattice energy is the breakdown of the force between the two of the ions in the lattice structure. So the two things are there, lattice energy and hydration energy. If hydration energy will dominate, substance will dissolve. If lattice energy dominates, substance will not dissolve. Right, then we have to heat it, we have to apply some other of the techniques. Okay, now come to the next one. We have the dissolution of the covalent compounds. If you remember that of the alcohol, here it is given. This is alcohol which dissolves in water by means of, you can see here the oxygen of water is attracting the hydrogen of alcohol. Alcohol is a covalent compound. It is ethanol which is shown here. Now what happens? There is developed hydrogen bonding between them. If you remember, hydrogen bonding appears when on one side there is present oxygen, nitrogen or fluorine, while on the other side there is present some small molecule, a small atom like that of hydrogen. Right? So here there is a formation of hydrogen bonding between the two by which it will dissolve in water. While it's this one region, it is termed as a hydrophobic region. It is not going to dissolve in water. Right? This is a hydrophobic region because the forces in it are totally different from those which are present in water. Water is a polar molecule, while in ethanol the OH region is only the polar one portion. It is hydrophilic portion. It loves to react with water, but behind it there is portion of hydrocarbon which is non-soluble part, or it is non-polar region, as there are present the weak van der Waals forces. It will not dissolve in water. Right? So a general term is here for the compounds that like dissolves like. Similar forces will attract similar molecules together. right? So here some of the compounds which are covalent compounds, they are soluble in water, while the others are insoluble in water. All those which have the polarity in them, they will a little bit dissolve in water, like alcohols, ethers, right? While, or but to say, some of the carboxylic acids, they also. But if we say they are present hydrocarbons, for example methane, for example we say ethane, benzene, they are not soluble in water because the forces between them are totally different. So you will find there are two types of the molecules in them, that is polar and non-polar. Polar will dissolve in water just like that of the alcohols, by means of hydrogen bonding in them, right? While the other covalent compounds which have the other forces in them, just like the methane or ethane or propane or benzene, they will dissolve into the similar type of the substance, that is maybe they are soluble in ether or acetone, etc., right? So this is how do they dissolve in water. Come to the next one. Next is the non-directional nature of ionic compounds and directional nature of the covalent compound. Here you can see in the structure, one after the other there is present cation, and then there is an anion. No particular direction. एक के बाद एक लगाते चले जाओ, लगाते हुए three dimensionally it will increase in size. So we say the, as it is only an attraction, electrostatic attraction between the ions, right? So ionic compounds, they are considered as rigid and non-directional. They can increase in any direction. So they are not allowed to move, right? They are not going to move, but whether you are going to heat it or not, it will take a lot of temperature or lot of energy to do so, right? So they are considered as a rigid one and non-directional compound. Once again, anions and cations, they have no particular direction to which they have to attach, but three-dimensionally they will go on attracting each other, right? But if you say, for example, look at this, it is a water molecule. We know very well that what is the direction of the bond? Hydrogen is directed towards oxygen, both of them, right? Similarly, look at this. Here you can see in ethanol, in dimethyl ether, in both the cases, there are particular directions of the bonds, right? They are not rigid, they are not non-directional, but they are directional ones, right? So this is what we say. These molecules, they can bend, they can rotate, right? So this is the difference between the bonding, between that of the ionic and the covalent compounds nature. Now look at this. This is telling you the reaction kinetics, that what will be the speed of the reactions when we are considering ionic compounds or the covalent compounds. Look at this experiment I have mentioned here. In one beaker I have dissolved sodium chloride, in the other one I have dissolved sugar of the same quantity in the same quantity of the solvent at the same temperature. Which one will dissolve first? Ultimately sodium chloride will dissolve first, then that of the covalent compound, that is the sugar, which is a covalent compound. So which one is having the rate first? Ultimately it is sodium chloride, which will dissolve first as compared to that of the sugar. So I will say that the rate of reaction of sodium chloride is high or fast as compared to that of the rate of reaction of sugar, right? So what we'll say overall, what the statement will be, that the ionic compounds, they go for the rapid reactions. Similarly, think about another reaction. What you have to do, this is what we say dissolution, or the reaction between that of the sodium hydroxide and HCl. A quick reaction occurs when we mix them both, right? And we get that of what we get. We get sodium chloride and water. The speed is so high, so fast. But if you think about, just think about digestion. आपने खाना खाया, the digestion of that food will take 3 to 4 hours. The reactions which are going on inside, they all are the, जो आपने खाया वो भी covalent compound containing था, वो organic compounds थे which you have taken. So they all are carrying covalent bonding in them. So the reactions are slow. right? Now here we have other examples, so many examples you can get it from the nature, that conversion of what you say, the water molecule from one state to another, that will require time, right? Breakage of the bonding will take time, and what you say, the photosynthetic process, that will need time. It will not occur so speedily, right? And these all are the reactions in which the covalent compounds, they have the slow speed. Now in this structure you can see three of the molecules are being mentioned here: hydrogen molecule, hydrogen fluoride molecule, and then sodium fluoride crystal is given. You can see hydrogen is having very small mass, right? But the volume occupied is very large, as you can see. Compare them all. Now, the density is related to mass upon volume. When the mass is small and the volume occupied is large, the density will be small, right? Hydrogen is a covalent compound, its density will be low. Hydrogen fluoride having a little bit small size, and its volume definitely occupied will be a little bit larger, less, as it is compact now, right? So what happens here? It is getting now less space. Okay, so its density will be higher than that of the hydrogen. Okay, although it is a covalent compound. Now come to the last one. Here sodium fluoride is given. Sodium fluoride will exist in the form of a three-dimensional crystal in which ions are held together by means of electrostatic force of attraction. The two compact structure is this one. Although the molecular mass is high, but the volume occupied is too low. So what will happen? The density will be highest one among them all, right? So this is what we say, the size and that of the volume, they are related to each other. Ionic compounds have less density, have high density as compared to that of the covalent compounds, as they are held together by means of the ions in the form of a compact structure. That's why, right? Now it is over today. The types of the crystals will be discussed in the next lecture along with the exercise. Okay.